We will start now with the second part of Licia Verde's course.
Okay, so welcome to the second lecture on statistical techniques. So what I want to talk about today is basically Monte Carlo methods and then discuss what it means to compute error bars of confidence level in this case, and introduction to go beyond the simple parameter fitting. So, but before we do that, let me recap a little bit some of the last thing we said yesterday. And so remember that we saw a table like that where there was the delta chi-square as a function of confidence level and number of parameters. And remember that there is a big difference, and I've seen grown-up people making big mistakes about this, between chi-square and reduced chi-square. Remember, the reduced chi-square is your chi-square divided by the number of degrees of freedom, right? Number of the data minus the number of parameters you fit. And you want that quantity to be of order unity. That is what I call the chi by I. In reality, you would have to deal with the Q function, which is a function of the gamma function, etc., etc. Now, don't take delta chi-square of the reduced chi-square, otherwise you're going to get nonsense, okay? Right. Now, you can make identification. I think it was sort of clear from what we said yesterday between the chi-square confidence level and the likelihood only for Gaussian or multivariate Gaussian with constant covariance. And it should be clear just from the definition of a Gaussian and the definition of your chi-square. And so keep this in mind when doing the interpretation of these sort of things. Now, I'm sure you all have seen things like that, but when you say that you describe a confidence region, you may have one or more parameters, and you will have things like ellipses, and you can imagine having like, a hill here, and you're going down the hill, and that's your chi-square of likelihood distribution. And so this is an example for the case from multivariate Gaussian. And this is just taken again from the numerical recipe Bible, chapter 15. Okay, so then a question yesterday was, okay, we put up the bias theorem, and there is on one case the posterior, and then on the other side the likelihood, and you show me an example of Gaussian likelihood, but you also told me that things are not always Gaussian, so what do I do in the general case? And so in the general case, you need to know your problem, and you need to know what is your likelihood, what is the probability of your data given a particular model or hypothesis. And so I'm going to show you here one example, and I will show you other examples if there is time, maybe next class. But you need to know your problem and then work with that, so there's no general description. So this is an example. So on how to work out what is the form of your likelihood. Let's take that you have the observation of n number of clusters, and that's a Poisson process, which we discussed earlier what the Poisson distribution is. And I mean, I could have done that with photons, and actually the original example was taken from this paper by Cash and was done with photons. But let's think in cosmological context. And so we write it this way, and we just say, well, let's just bin our observation, and then I is the number of clusters serving the I experimental bin. You can make bin in mass, or you can make bin in ratios. And so the expected number that you have in the bin, it's written by that, where this is your experimental bin. Again, mass, acid decrement, X-ray luminosity, redshift, or whatever. So you can define what in the original paper is called Cash statistics, which is minus 2 log of the probability. Now this sounds a lot like a chi-square because I'm taking a log of a likelihood, which is very similar to a chi-square. And you can write it this way. And so if you write it this way, now this is the total expected number of clusters in a given model, and this is your distribution of this II. And so either it's a bin or you take small bins with occupancy of 1 or 0 only, And then it basically turns out that the delta C between two different models is chi-square distributed. So you started off with something that is in Poisson, and you work out exactly what kind of likelihood you need to use. So that's an example. The other thing I want to start introducing and mentioning is marginalization. So let's say that you have a posterior distribution that depends on several parameters. Say you have the lambda CDM model and you have omega mater, Hubble parameter, omega baryon, etc., etc., etc. But you are only interested in the best fit value and the confidence region around omega mater, regardless of all the other parameters. And then it follows from what we define, from the definition we had about probability, that the way of doing that is simply to integrate it over all the other parameters, the one you're not interested in, and only leave here the parameters you're interested in. In my example, it will be just alpha 1, so j is equal to 1, and that's omega mater. Okay. Now, I'm paying frequencies or I'm paying Bayesian here? Should be an easy question for you. Exactly, I'm integrating over parameters. So basically, I'm integrating over an hypothesis that must be Bayesian. Frequencies will never do that. Okay, so let me show you, for example, a visual example of this, which in many cases you can find. You have one parameter here, one parameter there, and these are contour of equal posteriors. And you can see, in this case, you may have what are called degeneracies. And so you can have, something that looks very rounded here, but as you go down, you get tails. And so in some cases you may say, I'm interested in the probability of this parameter regardless of this other parameter, so you want to integrate out this other parameter. Okay, so the other things that follow for practical application from everything we said so far about the properties of probabilities and how to deal with priors is dealing with extra data sets, right? So you have a data set, you've done your analysis, and then you have another data set and you've done your analysis. How do you combine them? Well, we know from the property of probabilities that if you have two independent processes, then the probability of the likelihood just multiply. And so the other way you have to think about that instead is that you can use some data set as your prior, so the result that comes from a data set as a prior of the parameters, but then combine with the likelihood that comes from the other data set. But again, remember, you multiply the prior by the likelihood, so you're doing exactly the same operation, it's just a different way of interpreting it. Okay? When you do that, please be aware of inconsistent experiment. Right? So imagine you find, so let me give you an example actually taken from the literature where there is no real inconsistency, but you can see where things are going. So this is again from a previous release of WMAP. These were the WMAP constraints in the plane omega mater sigma A. And these were the weak lengthening constraints. Now, these two data sets are not obviously inconsistent with each other, right? The two sigma of one overlap with the one sigma of the other one. But still, when you combine them, you get this region here. And this region here looks smaller than it would have happened if the center of this one sigma would have coincided with the center of this other one sigma. Right? And so, in general, before you combine different experiments with something like that, make sure that they give you consistent answers. Otherwise, you're going to be getting nonsense. Okay? Good. Okay, now that we've cleared this, let's move on into Monte Carlo method. So, first of all, why are they called Monte Carlo? Well, Monte Carlo comes from actually Monaco, or Monte Carlo, where all the casinos are. So, you know where they come from. And also there's Formula 1, but that's nothing to do with it. So there are two very common applications of Monte Carlo method. And one is called Monte Carlo error estimation, and the other one is Monte Carlo Markov chain, or Markov chain Monte Carlo, or MCMC. Okay? So as a first introduction of what it means Monte Carlo method, let me show you that you should be familiar with this, because your brain does it all the time. And an example of this are these games where you have two complicated pictures and you have to spot the difference between two pictures. And it takes you some time to actually spot the difference between two pictures, because the way your brain works when it's put in front of a complex image is to sample the image. And so it samples the image, and from this sampling reconstruct the image itself. And so that's why you can have this kind of what is called blindness to some particulars, because the brain just samples the image, and so you can miss some of the details. And so, okay, so let's go into this in a little bit more mathematical footing. So, introduction to Monte Carlo method. Let's give ourselves a very simple problem. What's the mean of a large number of objects? Like, what's the mean height of people in Puerto Vallarta? Now, what you would have to do that, you would have to do sum from I that goes from 1 to n, where n is the total number of people in Puerto Vallarta, of the height of each of them, and then weighted by the total number of people. But if n is very large, this is untractable. So it's the same thing that your brain does when it gets put in front of a very complicated image. Oh, this is so complicated, I can't treat it exactly. So, but if you can get a fair sample, that is some sample of this big n, and n is small, but it's a good sample, then I can approximate this by this. And if I choose my sample properly, this is a very good estimator of this quantity. So that's everything there is, the fundamental motivation of doing Monte Carlo. So let's just write this in terms of probability. So when we define means, right, in probability, we say that it's an integral of your whatever, f of x, multiplied by the probability of x, and then integrated, okay? And so you can simplify this if this problem is too complicated by saying, well, instead of doing that, let me do the sum over a subsample S of size big S of this. And as long as the way I sample X belonging to the subsample little s, this is similar to P of X, then I'm okay. And so in Bayesian inference, you can rewrite this by saying, if I want my probability of a set of parameters given the data, I need to do this sort of integrals. And sometimes, and then instead of doing this complicated integral, I just do, a Monte Carlo integration. It's exactly the same thing. That's where Monte Carlo comes from. So again, the key is to choose your sample in such a way that it reflects your probability distribution that the one you wanted to integrate over. So you can show that by doing something like this, your estimator is unbiased, and you can quantify the variable that is the error of your estimator, and you can show that this error shrinks like S, which is the size of your subsample, to the 1/2. So the variance shrink like S. Cool. So let me go on and give you another very simple example. That is the classical example that we've always given when people get introduced to this kind of problem. Let's try to find the dark approximation of pi. So you know that if you draw this square and then you draw the red area, then pi is 4 times the red area if this square is the unit square. So you can say, okay, then my probability x, y, it's something that it is 1 if it's in here and is 0 otherwise. And then I just start dropping random points in there and then just count how many are in and how many are out. And then I can try to compute pi in this way. Now, if you try, you will see that this method is not that good to compute pi. There are much better methods to compute pi. So use Monte Carlo method only when needed. If there may be for specific problem other methods that are much better suited. But there is a whole suite of problems where actually you don't have other methods, or other methods will be undoable or untreatable, and then Monte Carlo is your way of going about it. Let me give you an historical note. And Enrico Fermi was finding very funny to astonish his colleagues by doing accurate prediction of what their experimental results were. And it is basically because he couldn't sleep at night. He was having insomnia. And so what he was doing Monte Carlo, to try to sleep instead of counting sheep, so people do that. And he was astonishing his colleague. And the Monte Carlo method really took off with the first computers. And you see that women were in charge of computers when this whole thing started. And with the development of the first atomic weapons. And I believe that still today, there is a lot of forefront research having to do with this, because of course exploding a bomb, it's a really expensive process. And so if you want to sample your possible parameter space of how you build a bomb or the dam and things like that, you want to explode the minimum number of bombs and learn as much as possible about what your parameters space does. Okay, so Monte Carlo error estimator. Let's go back to parameter estimation and confidence region. And let's reinterpret with the conceptual interpretation in cosmology. So let's say that there is alpha true, which is a set of cosmological parameters only known to Mother Nature. Okay? And this set is statistically realized in the observable universe. And so the observable universe has got another set of cosmological parameters, which are not necessarily identical to alpha 2, but are taken from the same probability distribution of that has got this as their mean. And then you do a measurement of the observable universe with this error, and you get a set of D0, which are the measured data. You analyze your data, and you get alpha 0. Now, this is all you, the experimenter, can see. And what you actually wanted to know, you wanted to infer something about alpha true and where alpha true came from. But this alpha 0 is not a unique realization of alpha true, right? For obvious reasons. First, because this is a statistical realization of this, and second, because you have some error associated with your measurement. And you want to quantify that. And so this is where Monte Carlo comes in, and that's what you really want. So there could be infinitely many realizations of, say, hypothetical data set, B1, B2, etc. Each one of them with best fit parameter instead of alpha 0, alpha 1, alpha 2, etc. So you would expect that in the limit where you consider many of these realizations, the average value of all these best fit parameters will give you back alpha 2. So if you knew the distribution of your alpha I for all these infinitely many hypothetical data set minus alpha true, that'll be all you need. Right? But that you cannot know. But what you hope you would know, it's something very close to that. Let's just say, or hope, that your alpha 0, which is the best set fit of parameters for your only data set that you have, which is D0, it's not too far away from alpha 2. And then in that case, you know you can simulate the distribution of alpha I minus alpha 0. And so if alpha 0 is not too far away from alpha true, then you can say that maybe alpha I minus alpha 0 is not too far away from the distribution of alpha true. So the game is make many synthetic realization of universes where alpha 0 is indeed the truth, like if it was alpha 2. Mimic the observational problems in all the details, in all these mock universes, estimate the best fit parameter from each, and map the distribution of alpha simulated on this mock universe is minus alpha 0. And this should give you an estimate of this distribution, which is what you wanted to know at the beginning. Okay, so this sounds simple after everything we say, but it's an extremely important tool. But now you see where the difficulty lies and where this kind of technique started becoming important with the advent of computers. This relies in making many synthetic realization of universes and mimic the observational process in all of them. And you want to have many of those in order to do statistics with them. So this is computationally very expensive, but it's extremely powerful. Is it clear so far? Okay, so I made it sound easy, but there's another key point that we really need to understand. That is, remember that when you do Monte Carlo, the key is that your subsample needs to be a fair sample of the probability distribution you want to sample. So, how do you know how to do that? How do you sample from the probability distribution? So, if you know what the probability distribution is, for some well-known univariate probability distribution, there are numerical routines that you can go and use. In other cases, there may be numerical technique that will allow you to sample P of X. But it's not one problem for which you have one solution. Okay, and the whole virtuosity of doing Monte Carlo method and Monte Carlo Markov chain relies on how to sample from the probability distribution in an effective way. Okay, so there is one thing that may be important for you to know, because it will come back over and over again because it's very powerful, which is called importance sampling. Let's say that you don't know how to sample from P, but you know how to sample from Q. And then you just say, well, I need to do this integral, so let me just multiply and divide by Q, and then just do my Monte Carlo this way. And then now I need to sample my exact sample of X from Q and not from P, which is what I know how to do. So this is called importance sampling, and it will keep popping up over and over again. What's the trick here? Okay, you want the Q to be well suited to P. So imagine P is very, very broad, and Q is just picked here. Obviously, that Q is not going to lead you anywhere, and you're going to get nonsense out of it. Or imagine that P is very, very big, and Q instead is very, very broad. Really good, but it's going to take you forever to actually get convergence, because you spend a lot of time where P is 0 and Q is not. So again, choosing your Q means knowing your P, means knowing the details of your particular problem, and there's not, a universal solution for this. So you need to know your problem. Okay. So is it clear so far? Okay. So let's move on to talking about Monte Carlo Markov chain. So say that you have a higher dimensional probability distribution, and in the philosophy of the Monte Carlo method, you want to sample in a way that is proportional to it. And the way to do it is with a random walk, although it's a special random walk. So the idea is you start at an arbitrary point in the parameter space and take Markov step. What means Markov step? It means that you only know depends on where you are, and that depends on where you were before. Okay? And so what you will find that you start from here, and imagine your probability distribution is here, so you start taking steps, and this region obviously is useless, which is called burn-in. At some point you start getting into business, and so you will start moving around, and then I didn't bother keep drawing the black line, so I just drew the points. And the name of the game is to make sure that the density of points is proportional to the probability that you want to sample. So that's your goal. So remember, because I've built it this way, the Markov chain gives you approximated, correlated sample from the target distribution when it's implemented properly. If it's not implemented properly, you don't even get that. So it's important to keep this in mind. It's not an exact solution to the problem. It's an approximate solution to the problem. But sometimes you can't do the exact thing, and so you have to deal with this and know how powerful it is and know its limit. Okay, for cosmology, there is an extremely useful software that is publicly available that is called MCMC, which is Cosmological Monte Carlo. And you can go on the web, download it, install it, and it comes with all the dependencies of all the possible data sets you can think of, and it's relatively easy to add your own, etc., and modify. However, using software as a black box is always a bad idea. So what I'm going to do next, I'm going to try to walk you through what's behind the black box. Okay? So you're still encouraged to open the black box in case you will have to use it. But at least you sort of know where to put your hand and what the black box is doing and what is the philosophy behind it. Okay? So, say you want to explore a multidimensional likelihood surface, and you want to do it with a grid-based approach, which is what you do, say, usually, or probably you've done in the lab at school with chi-square. So let's take an example where you have two parameters and you have, say, omega matter and sigma 8, and so you do a grid, say a 10 by 10 grid, you have 100 points. Fine. What if you have 6 parameters instead? And you know, and 10 by 10 is a coarse grid that maybe you will want to do it finer to actually get to know your probability distribution like that. But what if you have 6 parameters? Okay, so say that 10 is not good enough, you want to do 20, you have 6 parameters, 20 pixels by dimension, so you have, quickly more than 1 million evaluation. Say that the evaluation of your likelihood or your theoretical model takes of the order of 1 to 2 seconds. It grows pretty quickly. And so this is what I say, if you can do the exact problem, do it, but in many cases, doing the exact problem may not be possible. And so that's where the approximated methods come in. Okay? So again, this is standard in CMP analysis in the publicly available Cosmology. So the idea, you want to simulate the posterior distribution. And so let's go back to Bayes' theorem, where the probability of the data, I now wrote it this way, but you shouldn't be worried, because if you think about it, this is exactly what you're going to get. So this is your prior, alpha is your set of cosmological parameters. Say if you're thinking in the cosmic microwave background, the cosmological parameters are what gives you the theory CLs, and your data are the measured CLs. This bit is the likelihood. And then in this case, again back to the questions before, we know that we can assume that the temperature map is Gaussian. The CLs, therefore, are not Gaussian, because they are basically the square of something Gaussian, but you should be able to figure out what that is. And so the name of the game is to generate random walk drawn from the posterior that are a fair sample of the posterior, or the likelihood. Okay, so again, imagine that this is your likelihood, and this we have sheep, and we have, what is this? It's probably a cow, and this is something that looks like a sheep. And so says that this is your likelihood of being a sheep, and says that this is your prior on the sheep class, and your prior is broader, so it includes lamb, and I don't know, and other four-legged animals. Likely, your posterior will be something like that. And so, remember what's going on here, and let's keep this in the back of your mind, because at the end I'm going to ask you a question related to this. So you want to do a random walking parameter space. At each step, you sample one point in parameter space. The density is sample point. You want them to be proportional to the posterior distribution. Now, this technique is fast because if before you needed of the order of 10 to the 7 likelihood evaluation, now you need less than 10 to the 5. And depending on how you do it, you can get better. Marginalization is also easy because before, marginalization was doing integrals, and doing integrals is always complicated. But in this case, since you're doing a Monte Carlo integration, marginalization is just project your point and recompute their density. You don't need to do a complicated multidimensional integral. And adding external data set is often very easy, and it goes again on very important sampling. And we'll see that in a minute. So if you have to build your own Monte Carlo code, how would you do that? And I can tell you how to do it in one slide. So start at and what I'm telling you how to do it is the metropolis hasting algorithm. There are other techniques to do that, but let's start with this and understand this, and then it's easier to sort of build on this and make it a little bit sophisticated. So you start a random location in parameter space, which you call the alpha all, set of cosmological parameter, and you compute your likelihood all. And then you take a random step in parameter space. So if this floor is the parameter space, you just take a random step. Okay? And now you have your new parameters and your new value of the likelihood. Now that's the trick. If the new value of the likelihood is better than the old one, so this is a better fit, accept, which means take the step, take and save. Then the new becomes old, and you go back here. Take another random step, etc. On the other hand, if I try to do this, and my new likelihood is worse than the old one, let's say I did that instead, and go down in this way, you draw a random number x uniform in 0 and 1, and depending what x comes in and the ratio of the likelihood, take it or not take it. So if I were always doing this, accepting, and in this case not accepting it, what I will be doing, I will just try to find the maximum of likelihood or the minimum of -2 log likelihood, and basically I will just try to find the best fit, and that's it. But the name of the game here is not just to find the best fit. The name of the game is to find the best fit and find the error bar. That is, you need to sample the posterior. So to sample the posterior, you need this extra step that says, give me the probability with which I go in the wrong direction. Keep going. Repeat. And I guarantee you that eventually you will get exactly what you want. So if you want to write your own Markov chain code, you can do it. That's all you need to do. Now, of course, things are never as easy. So what it means take a random step? We need to specify that. So well, there is a theorem that says regardless how dumb your random step is, as long as it's random, eventually you will get a Markov chain. The key is eventually, right? Because you want to have a solution to a problem that it was too long or too complicated to solve in other ways. If you do it in a dumb way, maybe here it takes you longer than with the exact one, and then it be the purpose, right? So the probability distribution of the step is called the proposal distribution. You should not change this once the chain has started, because otherwise it's not exactly a chain, but there are ways that allow you actually to adjust this as you go on and still do statistical inference out of chains. So the proposal distribution, or what between me and you we call step size, is crucial to the MCMC efficiency, where efficiency means sampling the posterior in a fast and efficient way. Steps that are too small leads to what is called poor mixing. If I take very, very small steps, it takes me a very, very long time to explore the entire likelihood surface, right? Steps too big gives you a poor acceptance rate. If I always take steps that are really big, I may miss the minimum or the maximum, depending which way you're looking at it. And so I may never take a step, and my chain will remain stuck. Because Because remember, you need to find a fair sample of the likely posterior surface. So these are examples. If you take a step too small, you're taking a lot of steps, you get a very high acceptance rate, but you get a very poor exploration. If you can take a step too large, you basically keep trying and never move. So this is step number, and this is the likelihood value. So the best is always somewhere in the middle where the chains move and you keep accepting things. Now, there may be complications because sometimes your likelihood surface is something like that. It's got this very long degeneracy. And when you take a random step, if you don't know this information, maybe your random step is something like that moves in this radius. And you can see there are a lot of possibility for taking wrong steps and spending a lot of time before you explore your full likelihood surface. And I hope you can see this. So these are some examples of the true distribution, right? This is even multi-peak. And then getting two small steps, and then you end up not exploring and finding only one peak instead of the two. Two large steps, and then in this, then you have a very poor sample, so what you reconstruct is very noisy. And getting the right step, and actually this is the target distribution, and this is what you get, which is really close to the target distribution. So that's the name of the game. And the other thing is what we call random step for statisticians and core transition operators, and we'll understand why we can interpret it as an operator in a second. And if you read the statistical books, they go on and on about the detailed balance. Detailed balance means that you should have the same probability that if you are standing here to try to take a step there, than if you are standing here try to take a step there. Whether you accept it or not is a different matter because that depends on the actual evaluation of the likelihood. Trying to take the step, this needs to be reversible, right? It needs to be equally probable. And you usually have problems of boundaries. So usually when you write your code, you need to tell your parameters what is the minimum range and what is the maximum range. And so it's a really good idea to choose your range of parameters so that you really allow, you're sure to include the region where the likelihood is reasonable and only cut the tails where the likelihood is really small. Otherwise, this is a problem and you end up not having a Markov chain. So when the MCMC has forgotten about the starting location and has well explored the parameter space, then you are ready to do parameter estimation. So here it is again, step number versus log likelihood, and you can see that you start from a random point, is a very bad fit, you quickly go to a point where it's a good fit, and then you start exploring. And this region here is called burn-in, you should throw it away. The other thing you should be aware of is the following. Let's say you take a chain, and you start it, and you let it go, and it looks more or less like this, and that's the green one. You start another one from a different point in parameter space, you let it go a little bit, and that's the red one. Of course, if you had only the green one, you would say, this is power spectrum, spectral slope, this is the amplitude of the primordial power spectrum. If you had only green, you'd say, well, the biscuit value is an S equal 1 and A 0.87. But if you have only the red point, you say, well, an S is maybe 1.04 and A is 1. Now, if you are dealing with the inflationary model, this will tell you something, but this will tell you something entirely else. So we're learning something here, and you should use a mixing and convergence criterion before you go on and do parameter estimation. Convergence and mixing criterion means not just that I got in a region of parameter space where likely it's okay, but also that I fully explore that region, and I'm not stuck in a corner. And so there are several different techniques to check your convergence and mixing, and here I show you one of them, but you can read the literature, and depending on your problem, you can decide to use whatever criterion will best suit your problem. So what is recommended in this case, which is called German and Rubin convergence, is you start with 4 to 8 chains at well-separated point in parameter space. And then what this is telling you is basically you do a comparison of the variance within a chain and the variance between different chains. When these two quantities are virtually indistinguishable, then you know that you fully explore the light surface. So this is what this criterion tells you. And this is relatively easy to implement. It's true that you need to start 4 to 8 chains, but with multiprocessor computer, it's really good because this is parallelized very easily. Just you run this and you run this and you don't talk to each other until we need to do this operation. So that's not a problem. Okay, so let me repeat. Unconverged chains are just nonsense. Never do parameter estimation for an unconverged chains because you're going to get nonsense. Okay, so metropoly hashing is not the only implementation. It's very easy to explain, also because I can explain running around the room and jumping around the room. But there are other options that, depending on your problem, may be better. And this goes under the name of Eve sampler, rejection method, Hamiltonian Monte Carlo, simulated annealing, though you don't get an MCMC. This may be useful in some cases. So I'm just going to leave the names up here, just in case you read, say, rings a bell, or in case you have a problem, you know that metropoly casting is not the only option. It doesn't work for you. There are other options. Okay, so other things to worry about when you do Monte Carlo macro chains. Beware of the degeneracies between the parameters. So in this case, we have omega cold, and in this case, we have the Hubble parameters, and these are CMB data. This is called degeneracy. It's actually one of the relatively bad ones. It's one of the relatively bad ones because it looks like a banana. Okay? Beware of bananas. So if it looked like an ellipse, it wouldn't be a good idea, a bad thing. And this is what Cosmology does for you. Okay? Because if it is an ellipse, you can always define a linear operation that is a rotation and a rescaling of the axis so that your target distribution looks like a rounded thing, and then when you look rounded, your random step goes extremely well and sample it very efficiently. But if this is a banana, the operation on the ellipse you do here will be different from the operations you do there. So you would have to change your prescription for taking a random step along your chain, and you wouldn't necessarily end up with a Monte Carlo Markov chain, so that makes things complicated. So, of course, having an ellipse that looks like this is much better than having a proposal distribution that looks like this. And so, doing this linear matrix operation will still help you even in this case. But sometimes you, the scientist, can do better than a blind method like this, and you say, well, why don't I reparameterize? If I now redefine my parameter, instead of taking omega cold, I take omega cold h squared, and instead of taking h, I take this quantity here, which is basically the position of the peaks, rather than the value of the Hubble constant. There is a one-to-one relationship between the two things once you give me a set of parameters. Then this cloud of points becomes this. And now this is much, much easier to sample and implement. Okay, so a Cosmology has the option of computing covariance for the parameters. So you find the axis of the multidimensional degeneracy, perform a rotation of the scaling, and to obtain a simple symmetric contours. This improves your efficiency by up to a factor of 10. So it's still a linear operation, so it won't work with bananas. Question for you, as I anticipated. Where's the prior? We use likelihood.
The lambda CDM?
Yeah, but in the entire prescription for running a Monte Carlo Markov chain, I only mention likelihood. But what you get at the end of it, I told you, is a posterior. I never mention prior in the prescription for doing a Markov chain. So where is the prior?
It's your bounds. It's your bounds, your parameters.
That's where, when one part of the prior comes in.
It's flat across those.
It's flat in what? So the prior, it's all included in you take a random step in this variable. When I say take a random step in this variable, I'm taking basically a flat prior in that variable. And what's my variable? My variable is it omega cold or is it omega cold h squared? In one case I have a flat prior in omega cold, in the other case I have a flat prior in omega cold h squared. So that's where my prior comes in. So the number density of points of a Markov chains is a sample of the posterior. But you have an extra information saved in there, right? Because at each point in your chains, you cannot just say this where you are, but you can also say the value of the likelihood at that point in parameter space. So if you say that little extra information, you have information with prior, the local density of point, and information without prior, the value of the likelihood at that point in parameter space. Okay, so in some cases you may wonder what's the effect of my prior. And so one possibility is actually to know the value of the likelihood locally. The other thing that the people have started realizing of recently is, well, maybe you can define a quantity that will tell you how much you learn after you introduce the data. So if I have only the prior, this is what I know. Now I add the data, and this is what I know. What's the difference between the before and after putting the data into the mix? And that will tell you really how much information you have and how much dependence on the prior you have. And so this is the expression in case you find it, but no. So once you have the output, the density of point in parameter space gives you the posterior distribution. To obtain the marginalized distribution, just project the points. To obtain confidence interval, you would have to integrate the likelihood surface, that is compute where, for example, 68.3% of the points lie. To each point in parameter space given by the Markov chain, give a weight proportional to the number of times you stay in the chain. And to add analysis from other data set, the nice thing is that unless, well, if this other data set does not require extra parameter, you don't need to run your chain. You can do important sampling. So you renormalize the weight by the likelihood of the posterior of the new data set, depending on how you actually compute this quantity on the new data set. However, again, if the new data set is not consistent with the old one, you will get nonsense for exactly the same reason explained before. But this is really good. You don't have to rerun. You run it once and then you can add other data sets at minimal cost. Okay, so in the next maybe 3 minutes that I have, let me mention what it means once you have a Markov chain to compute errors, because different codes and different papers report different errors, and then sometimes you may look, oh, same data set, different error bars, what's going on? Well, it depends what error bars we need. So if everything was Gaussian, then we know how to compute the errors. But things are not always Gaussian, and we've seen obvious examples like, that banana-shaped thing that we drew before. And so this is an example taken by this paper. This is the number of effective neutrinos species, and this is basically your posterior, right? The height of your posterior. So what the Cosmology does, it computes what is called the central confidence interval. So it computes the mean, and then it computes some symmetric region around the mean that encloses 68 point whatever percent or 99 point whatever percent of everything under the curve. So if everything was Gaussian, this thing will coincide with the peak, right? But honestly, look at this. This point that you report as your best fit value is not actually the more likely one, because the more likely one is actually there. And also, this is symmetric, which is good, but the value of the posterior here is definitely not the same as the value of the posterior on the other end. So this may not be satisfactory when you actually have highly non-Gaussian distribution. Another option is what is called the Bayesian minimal confidence interval. That is, you go here in this case on the maximum of the posterior, and then you say, let me cut this, and then integrate until I arrive to 68.3 or 99 point whatever. And then I report this as my central value and this as my error bar. Now the error bar is not symmetric anymore, but maybe this is closer to what you would intuitively want to know as your best fit and your confidence interval. And there are other options of actually doing it before marginalizing and actually looking at the maximum of the posterior in the multidimensional space rather than marginalize first. Because here it is. This is one example, again from the WMAP data, omega k, okay? The maximum of the multidimensional likelihood is here, but once I marginalize, once I project, then the maximum shifts there. And so there may be different best fit depending on what quantity you want to report. So keep that in mind. Let me go back to the prior and then I'm done. So once you have, if you want to figure out how much dependence on the prior there is, an easy thing to do is you take your output and you look at the value of the likelihood and not the weight. And if you have some uninteresting parameter, what you may want to do, you may want to do the profile likelihood ratio. That is, say you have an interesting parameter and one that you're interested in, say the sum of neutrino masses. For each value of the sum of the neutrino masses, find the maximum likelihood regardless of the value assumed by all the other parameters, and then consider this ratio as a function of the sum of neutrino masses. And this is an example from this paper, and if you consider WMAP 5 only, then we have the crosses, and the line is just fit to guide your eyes, so you should look at this. And this is much closer to what a frequentist would want to see. The name of the game is, if your prior is not that important, doing your confidence level this way or doing them this way should not be too different. If it is really different, then you're seeing the priors, you're not seeing the effect of the data. Okay, so if you want to play with an output of a Markov chain, if you don't have time or a supercomputer to run it while you are here in Convergence, you can simply go there and you can download the output and then you can play with it. And there is even an interactive plotting routine when you can just go there, choose the parameters you want, and it will just plot it for you. So you can go there and have fun, and I think I'll stop here because otherwise I'm out of time.
Time for a couple of short questions, please. Over there.
Okay, this question is regarding importance sampling. I was wondering if you could give an example of, like that we use in cosmology, of where we know Q, but we don't know P, and they're sufficiently well fitted to each other that we can implement this.
So one of the suggested exercises, it's very close to that. So let me just mention it. Okay. Say you have a WMAP chain, and say you want to, you have confidence limit, few parameters, etc., and now say that you look at ASCO pH and you realize, oh, there is a really good measurement of H naught, and I didn't know that before. So imagine I wanted to do WMAP plus H naught, but I did WMAP alone, so I didn't do the P for H naught also, or P for, and I want to add it. So what do I do?
Okay, so you could probably just do that.
So you simply resample. At that point, you resample, you reweight.
Okay.
And that's it.